So as Joe mentioned, the best thing to do always when we're switching from tutorials is to go to File, New Blank, just to avoid any issues from previous simulations. And then we're going to go ahead and go to the Tutorials menu and click on Tutorial 3, Multi-Scale Network. So this network model represents a simplified cortical network. So we're going to see that it has 3 layers, only 60 cells, so it's very simple. And it also includes Rxd components. So it has the calcium ion, the potassium ion, and some reactions that we can see later. So let's first explore a bit the different components in this third tutorial. So for cell types, we have 2 different cell types, excitatory and inhibitory. We can look at the sections, and we will see that they are simplified cell models, so they only have 5 compartments. The inhibitor is actually a bit simpler, and it only has 2 different compartments, 3 compartments, soma, axon, and dendrite. But they do have, for example, if you go into the excitatory, click on sections, and go into mechanisms, we can see that they have a number of channels, including calcium channels and some potassium channels. This one in particular, KBK, it's a potassium channel that depends on calcium, so it's activated by calcium, and that will play a relevant role in this example. If we move on to populations, we will see that, as I mentioned, it has these 3 different layers. So layer 2 with two populations, excitatory and inhibitory, layer 4, and layer 5. So excitatory and inhibitory in each of the 3 layers. We click on them, we can see that we only have 10 neurons in each one. And something interesting in this example is that we have a defined spatial distribution. So this means that you can place cells, although they will be placed randomly, you can constrain the spatial distribution of these cells. So in this case, because we wanted to separate the different layers, we specified that in the y-axis, that we assume is the cortical depth, for example, layer 2 cells will be placed between 50 and 150 micrometers. This is just an example, it's not meant to be exact. And if we go to layer 4, we click on spatial distribution. We will see that in this case, cells will be placed within a depth of 150 and 300 micrometers. Okay. Another way to specify this is using, so if we click on layer 5 in E5 and go to spatial distribution, we will see that another way to specify the depth limits are using normalized values instead of absolute values. So you can select this in this drop-down menu. And in this case, you can see that it's, cells are placed between 0.6 and 1. So this represents a normalized value based on the dimensions of the network that we're building. And those dimensions are specified elsewhere. So if we go to configuration and click on network attributes, we will see here the dimensions of this network. So we see it's a 100 micrometer by 500 micrometer depth and 100 micrometer in the depth dimension, in the other horizontal dimensions. So X and Z would be the horizontal dimensions. So you can change this here, and you can then define the different volumes where the cells will be placed using either normalized or absolute values. So synaptic mechanisms, nothing too different from the previous one, to an excitatory and inhibitory synaptic mechanism. In connectivity rules, though, we do have something a bit more complicated in this example, which uses this idea of defining mathematical expressions to specify different properties of the connectivity. So if we scroll down, we will see here in where it says the weight of the synaptic connection, and this was something that they were asking in the chat. So this has been defined as a function of one of the properties of the cells. In this case, the postsynaptic cell normalized cortical depth. So these variables are built into NetPyNE, and you can use them in these mathematical expressions. There is a list of the variables available that you can use. You can use things like the X, Y, Z locations of cells. And you can use, for example, the distance between cells. So in this case, the mathematical expression will make the weights of cells that are deeper within this cortical column that we have, the weights will be stronger. So the weight of the cell depends on its cortical depth. And these kind of rules are things you can find in experimental data. So this was inspired by some data we got from mouse layer 5B, where the inputs from layer 2-3 depended on the depth of the layer 5B cells. Another example of this is the connection delay, which in this case depends on the distance, the three-dimensional Euclidean distance between the pre- and postsynaptic cell, this variable here, and the velocity of propagation, which you can also specify in NetPyNE. So all this is explained in the documentation. If you go to the tutorials, this is actually tutorial 5, the network itself, and you can see how all these things are defined. So I think that's more or less the most relevant things here. So again, mention that this, let's just go ahead and click on Create Network, and I will explain a bit more while it's running. So this takes a bit longer because it's a 60 cell network, and also each of the cells includes Rxd components. So now we have the cell here, the network's instantiated already. So if you zoom in, we can color the different cells to see them more clearly. We see that we have these two different cell types. The excitatory cell is a bit thinner, has a thinner apical dendrite, where these inhibitory cells have like a thicker apical trunk. We can also, for example, color specific populations. If we want to see only layer 2, we could say color this, here, color this in red. So all of them would be the same color, and we could identify them more easily. And we can also, we didn't mention before, but you can hide and show different populations, or center the view on a specific cell. If you wanted to find a cell in your network, you can click on the zoom icon, and that directs you there. So I'm going to go ahead and run the simulation, because this does take a bit longer because of it simulates 1 second, and due to the Rxd component, it's a bit slower. So it actually takes 1 minute and 20 seconds. So I'm going to click on simulate and leave it there. And I'm just going to explain the reactions that are implemented in this model using Rxd. So if I go back to these tutorial slides, I hope you can all see my screen still. So we simulated 2 different regions, 3 different regions actually. So we have the extracellular space outside of the cell, we have the cytosol, and we have the endoplasmic reticulum. These are 3 regions in Rxd. And the sort of multi-stage reaction that we're simulating here begins with an increase in the IP3 molecule in the cytosol. And this, although this step is not implicitly simulated, this can happen due to metabotropic glutamate receptors. And so this result in increase in IP3 opens the channels of the endoplasmic reticulum IP3 receptors. This in turn releases calcium from the inside of the ER into the cytosol. This calcium in turn activates the calcium-dependent potassium channels, which results in an increase of potassium current, which results in less firing in the cell. So this hyperpolarizing potassium current reduces the cell firing, and so this reduced firing in turn results in less activity in the whole network, and the Lfp signal, of course, reflects this reducement in activity. So to illustrate this process, what we're going to do is first, so this is still running, but I think it should be almost done. So you will notice that in the menus, we actually have two versions of the tutorial 3. One of them is with a low initial concentration of IP3, and the second one with a high initial concentration. And the idea is that by loading each one, you will be able to compare the activity resulting from each of them. And so it illustrates that a small change in the concentration of one of the molecules affects the whole network activity and the Lfp signal. So now the simulation finished. So the first thing we can have a look is this connectivity matrix. And we'll see that one of the interesting things is that the connectivity from excitatory cells to excitatory cells, we define them using this rule where the weight was stronger for deeper connections. And so you see here that layer 5 excitatory cells receive a much stronger input than layer 2, and layer 4 is in the middle. So we see that with a simple connectivity rule, we were able to define a relatively complex connectivity profile. For the inhibitory connectivity, I didn't show it, but it has a rule that says that connectivity should be mostly local. So you see, although this is still random because we have random probabilities of connection, but you see that connectivity is quite strong from inhibitory cells to excitatory cells in layer 2. Also relatively strong from E4 to I4, and from E5 to, from I5 to E5. So this is also based on the connectivity rules. From I4 to E4, I meant before. So these 3 squares. So let's go ahead and show the different plots that we have here. So this is the connectivity as a 2D representation with the connections shown with lines. And this, you can see that more or less represents this very simple cortical column where we have the cells are located in the locations specified by these Y ranges that we specified before in the population. So the layer 2 cells are only in the upper section of the cortical column, layer 4 and layer 5. Can go ahead and look at the different traces that were recorded. In this example, we not only recorded the voltage summa, but also the intracellular concentration of calcium and the extracellular concentration of calcium. As well, we recorded the potassium currents that you can see here. So in this case, we had this low IP3 concentration at the beginning, which means that the calcium level wasn't high enough to activate these potassium channels. And so the activity of the network is relatively high during the whole period. So if we look at the raster plot, we see activity during the whole second and almost some of these oscillations due to the excitatory and inhibitory interactions. So let me just show this. Guys, okay. Put this here. And the other interesting thing that we can look at here is the Lfp signal that we recorded. So here we placed electrodes in 3 different locations in the network. So you can see that 3 different depths. The white one at the top is the average of the 3 electrodes, and the other 3 are in layer 2, layer 4, and layer 5. We can also plot the power spectra of this signal. Let's see, maybe we can close this one, make this a bit bigger, and show the Lfp signal next to the Lfp plot. Maybe we can show the traces down here. So this configuration for the plots allows you a lot of flexibility to place the plots in different locations. Make it a bit bigger. And the other thing that we can have a look here is the Rxd concentration plot. So this is the concentration of calcium in the extracellular space, which was also recorded in this network model specified using the Rxd components. And we can see here that the concentration of calcium decreases at the different neuron locations because it's being used up. So this is an example of looking at, let me just plot the Lfp signal. Okay, so we're looking at different scales of the network. So we have both the Lfp signal here, the power spectra of the signal, as well as the concentration of one of the molecules in the network model. And we can also have a look at the actual spectrogram of the Lfp signal, which gives us the, let me show this a bit bigger. Okay. So the time evolution of the Lfp signal. And we can see, for example, that is a clear, strong signal at around 20, 30 hertz. Okay. So just keep in mind the results that we're looking at right now. So we have this continued activity for the whole second of simulation. And what we're going to do now is create, again, a blank model just to clear out this one and load the other version of this tutorial where we have a high IP3 concentration from the beginning. And we're going to see how that affects the calcium concentration and, in turn, the activity of the network. So if you want, for example, you can make a screenshot of this if you want to keep track of how it looked. One of the key components to look at are these voltage traces here. Okay, so if everybody's up to speed, I'll just go ahead and clear this one. Blank. Okay, so now we have a blank one, and we want to load tutorial 3, but the version that's right at the bottom that says multi-scale network high IP3. So the only change that happened here is we set the initial concentration of IP3 from 0 to 0.1. That code is not actually reflected in the GUI because we are still working adding the Rxd components to the GUI, and that should be ready this year, hopefully. But you could potentially go to the Python console and explore the parameters. I'm just going to show this for illustration purposes, but you don't need to do it. Peto, net params, Rxd params. So all the reaction diffusion params are stored here. It's a big dictionary. And we can check the different components using keys. And I believe this parameter is in constants. So we see here this value that says IP3 init is 0.1. And if you check this same value in the previous simulation, it would say 0.0. That's the only difference here. So let's go ahead and simulate the network and close the. I can paste this in the chat in case someone wants to check it. Well, I don't see the chat right now, but I'll paste it later. So let's create the network. and run the simulation in the rocket. And I'm gonna try to show the code for this tutorial. Can you see my screen, the code that I'm showing? Maybe I have to share it differently.
I can't see it.
So let me share again. Can you see it now?
Yep.
Okay, great. So yeah, so this is, I will show more about how to write NetPyNE models using code, but this is all the code required for this model. So we have a bunch of components here defining the network, the different cell types, the populations, the synapses. So as you will know, is a very similar structure to what you're seeing in the GUI. So it's structured with these 7 different components, the stimulation parameters, the 2 connectivity rules that we were looking at before in the GUI, and from here onwards are the Rxd components. So we have a bunch of constants that are defined. We have regions, as I mentioned before, we have the cytosol and the extracellular space and the ER. We have the calcium and the IP3 species. And we have states and reactions that I'm not going to go into details, but basically they represent that multi-stage reaction that I showed before in the slides. Then finally, we just have what we call the simulation configuration. So things like what do you want to, what's the duration of the simulation, the initial voltage for the cells, what you want to record. Oh, and this is all extra stuff that we were trying out, so we can remove that. And here at the end, just the number of plots, that we want to show for the simulation. So this is in total like 160 lines for the full definition of the model. Okay, so if we go back to the model itself now, we see here the network as before. And if we now plot the same plots we were looking at before, so let's look at the cell traces, we will see a difference here. And due to this high IP3 concentration, after about 400 milliseconds, the intracellular concentration of calcium starts increasing quite fast. And this is due to the release from the ER of calcium into the cytosol. So this results in the potassium currents being higher, and it results in less spikes. So if we look at the raster plot, we see that the activity dies off at the end of the simulation. This is the spike histogram. So let's look at the Lfp signal, and you can see very clearly that after 500 milliseconds, the activity of the Lfp signal is reduced. Same thing in the spectrogram. You have this very clear oscillation around 30 Hertz, and it dies off at the end. Okay. You can also plot the Rxd concentration as we showed before, the extracellular concentration of calcium. And I think that's the main thing for this tutorial. So just illustrating how changes at the molecular level is affecting the spiking of the cells, and in turn, the whole Lfp signal recorded from the network.